the SDO Marathon Body 219. My name is Nicole, Fierro. This is Vanessa, Hawkins, Lazaro, Carballo, and Rodriguez. Our advisor is Dr. Andres. So there are many problem statements for this project, the main ones being a renewable energy alternative to fossil fuels, so we have a battery-powered vehicle. One of our main concerns is also efficiency, so we need an aerodynamic design, along with the use of composites to increase strength while decreasing the weight of the vehicle. With these, we hope to have competitive placing in the 2017 SDO Marathon competition. The history of the competition, it started in 1939 with a couple scientists who wanted to see whose car could go the furthest with just 1 gallon of gas. Now, there's 3 different continents in the competition, along with 7 different fuel types. The current record is set by a Swedish team in 2005 with hydrogen fuel cell technology. The purpose of the competition, according to Shell, is to challenge students to build energy-efficient cars that can travel the furthest with the least amount of energy. We hope to achieve this with a drag coefficient between 0.15 and 0.25, a lightweight body design, minimal composite use while still having structural integrity within our manufacturing capabilities, and a low cost of maximum $5,000 for the body of the vehicle. These regulations were set by the SDO Marathon rule book. These are regarding the size and the weight of the actual vehicle. We also have some safety constraints we need to take into consideration. The driver of the vehicle needs to be able to get out in 10 seconds. The electrical components of the car need to be easily accessible. Along with the driver needs to have a 180-degree view of everything around them. So we do need to install windows and we need rear view mirrors. These are some of the many things we need to take into consideration in constructing the body of the vehicle.
So moving on to some history on electric vehicles. First of all, an electric vehicle is a vehicle which is battery powered. Robert Anderson, a Scottish inventor, created the first electric carriage. However, in present day, this would not be seen as practical because the battery used was not rechargeable. So Thomas Davenport, an American inventor, created the first practical EV. This EV is very similar to the ones we use today, as in we use lithium-ion batteries to power our vehicles now, which is rechargeable and practical in today's sense. So our vehicle will also be using this type of battery, and it will be handled and programmed by an electrical and computer senior design team. So when deciding what the shape of our body should look like, we had to take aerodynamics into account. So in this figure here, you see an example of a good and a bad shape. The top shape shows a laminar flow because of the gradual inclines and declines, and the bottom shows a very bad design because of its turbulent flow creation and drag. So this is what we need to avoid when creating our design, which should be laminar and a teardrop aerodynamic shape. So design alternative 1, which was one of our first designs, features a low drag coefficient of about 0.2 and an aerodynamic teardrop shape. The disadvantage of this design was that the rear wheel was exposed, disrupting our airflow. To our second design, very similar to our first design, we had gradual inclines and declines, maintained the teardrop-like shape, and also had a low drag coefficient of also about 0.2. The disadvantages of this design were that, again, the rear wheel was exposed, and that the end was very sharp, making it hard to manufacture within our team's capability. Design alternative 3 in our final design is attempts to correct all of these previous cons mentioned. It covers the rear wheel, maintains the aerodynamic shape, as well as staying manufacturable within our means. The disadvantage, or more the opportunities for improvement, are to make these angles from the side to the rear shallower, as well as decreasing the use of excess space around the areas of the vehicle, such as the rear wheel. So moving on to simulations, in order to improve and optimize our final design, we had to use SolidWorks to simulate pressure surface plots, turbulence intensities, flow of velocity, as well as other simulations. So here you see the pressure surface plot of our first design. As you see on your left, the pressure scale is very shallow, showing that the pressure is not only uniform, but also close to atmospheric pressure. Here you see an example of a turbulence intensity plot for the first design. What we wish to maintain here is that these blue lines stay very parallel throughout, keeping the laminar flow. And lastly, the flow of velocity. For this, we set an initial velocity of 30 miles per hour, which is the maximum output speed of the motor, or 13.41 meters per second. And this was done basically, even though the vehicle will be going an average of 15 miles per hour, we wanted to set the situation in the worst case scenario to make sure that it could handle the situation in any event.
The floor of the vehicle is going to serve for structural purposes. As she mentioned before, the driver has to stand up and get out of the car in 10 seconds. So we're going to save way, we're going to design half of the floor for a structural purpose and the other half to save weight with less amount of layers. On the carbon fiber, that's the material we are using because of its lightweight and strength. This is the load condition that her getting out of the car is going to be present on the plate. As you see, it's going to be two bending moments in the two directions that we are exposing here. Now, for the carbon fiber, we came up with research. Right now we are researching how we're going to calculate the amount of layers that we're going to use and the direction of each of the layers. So far, under our current load condition, we're going to be dealing with transfer deflections. So we have to calculate the maximum momentum that our design is going to have. So the maximum momentum is related to the maximum curvature through the bending stiffness matrix. This bending and stiffness matrix is going to depend on the material, the type of carbon that we're going to use, and the direction of our layers. The maximum bending, allowed bending, is going to depend both on the material direction, but also on the boundary conditions of the floor. So we are working very close with the chassis team to see how we're going to clamp or what type of boundary we're going to attach the floor to the chassis. As a second design to take into account, we're going to do calculation to avoid delamination. The lamination is going to be very related with the manufacturing process because it can be induced if the manufacturing process is not on point, it's not really good. It can induce initial spots of delamination, but also the lamination can cause a reduction of the stiffness. So the previous value of the maximum momentum can be really lower than the one that we calculate because of the presence of delamination.
For the manufacturing of the body, right now we're currently looking at composites. The reason is because they're lightweight and strong. Specifically, we're looking at carbon fiber. Because energy efficiency is the name of the game, composites are ideal for us. For the floor of our body, we're interested in doing composite core sandwich. The reason is because we want the drivers to be able to stand and sit on the floor, unlike last year where they had to tiptoe around and bring a couple forward. For the manufacturing method, currently we're looking at pre-preg/autoclave. The reason is because we will get a higher quality of parts, and also the manufacturing time behind it will be rather quick compared to a pan layup or resin fusion. For our global design initiative, we have decided that all video presentations and documentations will be provided in English, Spanish, and German. Also, all calculations and measurements will be provided in SI and English units. And lastly, we are trying to use materials in our project that are widely accessible throughout most regions of the world. Our survey-related standards is the 2017 show Eco Marathon Global. There were several criterions that we had to abide by, but there were too many to list, so here are some. One is that the vehicle must be fully covered, and the second being that the vehicle must have a track width of at least 50 centimeters. This is our Gantt chart. For the most part, we've been very successful in sticking with the timeline of our Gantt chart. The only exceptions would probably have to be manufacturing, where it's very time-consuming, and so because of that, because of our schedule, we haven't really had the time to go in depth into manufacturing. But currently, we're gearing up to start in December, should I say, and we're looking at probably finishing up if everything goes fine and smoothly around January. Some of the things that we've taken away from this project is, for example, we have gotten an insight into some of the challenges that a company faces when producing a product. In this case, it's a composite product like prosthetics. We have also gotten a good grasp on just how widespread composites are, specifically carbon fiber. It's pretty much in just about every single industry you can think of. And lastly, we've also had to reach out into several different areas that we did not really think we would need to reach out. Specifically, aerodynamics. As we got more serious about making a competitive car, we realized how just important the aerodynamics is for such a vehicle. And to conclude, again, there is a high demand for efficiency and durability for composites, especially now with all the regulations where there's a greater need to haul around more load but with less weight. Also, piggybacking on what I just said about the Gantt chart, we also have more work to do with our final design. As you may notice, there was some excess space, as well as the angles were not steep enough, so that might create drag. And also, finally, like I said, we have to start gearing up for manufacturing in the summer.
Thank you.
Thank you.
So what happens when you're done curing the carbon fiber, you pull it off the mold, and you remove a ply? Do you start from scratch?
Probably would have to start from scratch because we would pretty much, the integrity of the fiber would be ruined, and that's something that we can't really, that's something that we can't deal with at competition because then you're going in there with a weaker part, and what happens if it fails at competition? That would be devastating.
So my recommendation is add a sacrificial layer, apply to your carbon fiber layup. So if you're using 12 layers, do 13 or 14.
Okay.
And that way you can afford to break one or two. That's what we do, which is pretty smart. It's a huge problem because we used to break carbon fiber layups all the time. My other concern is that you're taking composites to a very analytical place, which is not a thing that actually is well understood. And my recommendation would be to lay up multiple samples of composite and test them, because your analysis isn't going to actually represent what you want to do. And considering that you're going to be moving at like 15 miles an hour, you said, honestly, like, I would just do like 45-degree plies, 90 and 0, and then however many you need to make sure your strength is what you need. And that'll probably get you what you need. I mean, you're not going to be experiencing crazy loads, so I would focus less on the analytics of carbon fiber, considering that no one really understands that, and more on understanding what it does when you actually cure it and how to test that. That's something that's very sought after in an industry that doesn't exist because people don't generally work with carbon fiber.
Yeah, we have been talking about doing empirical testing. So an actual building a sample of laminate and actually testing it. Again, we just haven't really done it.
Yeah.
We'll definitely around December.
When we started, we were going to do hand layover, we didn't know how to go about it, but then one of our professors offered an autoclave for us. So we're still going between those different options for manufacturing, between things that we can actually do. So that's what we're working on right now.
Also for the cost analysis, another reason why we want to go with pre-preg is because we have some contacts and they will be willing to offer us at least a discount for the pre-preg. So it's definitely a lot better than just buying the pre-preg fresh off the supplier, right?
Just 2 words of advice. When you go to your supplier for carbon fiber, ask for a sample of their carbon fiber and cut it in half. I deal with composites and we've seen a lot of issues with bending of the plies or abnormalities in the plies, which would decrease your material properties. So just understand what might be the quality of the material you're purchasing before you actually commit to purchasing it. And the second is, this was mentioned on a previous senior design, is make sure you have the proper safety measures inside your vehicle, whether it is a fast way of getting out, a roll bar, something to make sure that...
there is a roll bar, it's mandatory.
We have a chassis set up already, but our main focus is the body, but we do have a whole team of focusing on another aspect of the vehicle. So we do have a minimal chassis that we're trying to cut down, but there is a roll bar, there is fire retardant material behind the driver to separate them from the power system. There's a lot of safety measures. Shell takes their safety very seriously.
fire
So
retardant-
we take that everything into
Fire
consideration.
retardant material that we're thinking of or have in mind is using again, another composite core of carbon fiber to shield the driver from electrical components. So we're thinking of doing can't really see it really here because should have actually done a cross-section side instead of a full-on figure. But it's a roll bar, and so we're thinking about doing the shape of roll bar, then on the sides of the core sandwich, doing a semicircle. So it's pretty much just a sweep of the roll bar. We still haven't figured out exactly how we mount it on there, but that is something that we are interested in doing.
I would be very wary of putting holes in your carbon fiber. That's, I think I've heard quoted like 50% knockdown in strength if you put a hole in your carbon fiber. And if you have certain imperfections, I think depending on the size, you're like looking at 20 to 30%. So I would be very careful how you mount that to your structure.
That's another area that contemplates.
If you need to, I would suggest like some sort of metallic brace that overlaps over the carbon fiber, and then you bolt through that so you strengthen the joints.
That's what the fastest car they use fiberglass, and that's how we attach the chassis to the fiberglass itself. That's what we were thinking of just sticking to for this year also. But since we do have to do half and half of the floor because of the autoclave restrictions and because of what I need to move the driver, we're still kind of setting up how we're going to attach which specific places to decrease the what we would lose from the carbon fiber.
And in addition, last year's body it was a composite body, but it had pretty much served no purpose aside from aerodynamics. Couldn't get, like I said, tiptoe around it. So they did like U clamps around the members of the chassis, but for ours it definitely had to be different because they just straight up just bolted through the fiber, the composite.
Any other questions?